Hello everyone, welcome to this course on Geophysical Fluid Dynamics. I am Ritabrat Thakur. I am a faculty member in the Department of Applied Mechanics and Indian Institute of Technology, Delhi. I broadly work and teach courses related to fluid dynamics. This course on Geophysical Fluid Dynamics is designed as a 12-week 3-credit course. This will delve deep into the mathematics and the physics of flows in the atmosphere and the ocean. This course will assume that you would have completed at least one course on intermediate level fluid dynamics. In this introductory video, I'll give a brief overview and motivation of why we need this course. This is planet Earth. This is where we live and multiple other species live. Approximately 70-71% of the surface of this planet is covered by oceans, and the whole Earth is covered by atmosphere. And because of the presence of ocean and atmosphere, we and several others and all the species that we know of can survive on this Earth. And geophysical fluid dynamics, as the name suggests, is a study of flows around us, that is, study of the flows in the oceans and the atmosphere. So GFD is a specialized branch that deals with naturally occurring flows. As I mentioned before, this consists of flows in the atmosphere and oceans, but also consists of other flows in large water bodies, for example, lakes. The objective of this course is to develop a rigorous understanding of such flows. The restriction that we place on the flow field is that the scales of the motions are large meaning a few hundreds of meters and above. This means that the continuum hypothesis of fluid mechanics will be valid all throughout this course. Also, as we deal with large-scale flows, there are two important factors that come into play. We'll be dealing with flows that are affected by the rotation of the Earth, as well as the variation of density, which is a function of temperature and salinity, with depth or height. So these are some representative questions of interest for someone who is learning this course. This is not an exhaustive list, but some questions, for example, how do ocean gyres and waves form? How do atmospheric hurricanes form? What are the characteristics of ocean currents and how do they change their structure? Does the depth of the ocean play a role in determining the dynamics of the waves and currents? How do atmospheric winds affect ocean circulation, and how does the ocean affect back the atmosphere? What determines stability of oceaning and atmospheric flows? What are the forms of waves in the atmosphere and the ocean? How do the ocean and the atmosphere become turbulent? How do they help in mixing different quantities, for example, pollutants or oil spills? Before going into various different areas in which this course can be helpful, let me tell you that this course is interesting in itself, even if we don't want to find any necessity in different areas of our interest. This course will give a broad understanding of the flows around us. But if you are looking for specific interest areas, this course will help in understanding or at least developing some intuition in going into ocean and earth systems modeling. So this will help in understanding the underlying principles which will be used in developing numerical ocean models, which are solved in computers, and numerical weather prediction models, which are prediction models or numerical codes for understanding the atmospheric phenomena. Given that weather and climate systems have been pushed to their limits of stability and we routinely see the effects of changing climate, a deeper understanding is needed to act on the triggering factors. Coastal hydrodynamics. Understanding wave dynamics and ocean circulation, tidal currents is critical in building offshore wind farms, oil rigs, and other structures. Harvesting energy from tidal currents and ocean heat also requires understanding of GFD principles. GFD is geophysical fluid dynamics. Environmental monitoring. Principles of GFD helps engineers in tracking smoke, chemical spills, greenhouse gases, and how they disperse through air and water. This is of importance to prevent loss of lives. Aerospace and aviation. Large-scale atmospheric fluid dynamics is important to design flight paths, to predict instabilities and turbulence, and designing structures which can withstand those. Structures for wind turbines and high-altitude flights and rockets. Designing and navigating oceans using uncrewed vehicles requires deep knowledge of ocean currents, tides, eddies, and density changes. Hence, this course can be important for both scientists and engineers. They will be aware of the complex multi-scale systems where thermodynamics, gravity, and rotation compete. And this will also allow for designing of small laboratory models, which will in turn inform the processes that are happening at a large scale. And these small scale laboratory experiments will develop intuition, develop deeper physical understanding, which will be further used for parameterizing those processes in global ocean or climate models, which have very large grid size and cannot represent those small scale processes. With this, I welcome you to this course. Thank you.